In this lesson, I'll show you how to find the resulting speed of two objects moving in the same direction. This is a conservation of momentum problem. The question reads, a 3,000 kilogram closed boxcar traveling at 3.0 meters per second is overtaken by a 1,000 kilogram open boxcar traveling at 5.0 meters per second. The cars couple together. In part A, find the resulting speed of the combination. We'll start with this and use our information to answer part B. So first of all, let's do a quick illustration. Let's pretend that this rectangle is a boxcar and it is moving, let's say, in the direction to its right. It has a mass of 3,000 kilograms and a speed of 3.0 meters per second. Then we have another one that's traveling at 5.0 meters per second, so it's faster and lighter. So let me just show another arrow where the other one is 1,000 kilograms and speed of 5.0 meters per second. Technically, according to the question, that once they reach each other, they couple somehow. I'm not sure how that happens, but they combine together. And so the combined momentum of the two boxcars should equal to the sum of the individual momentums. So if we represent momentum as P is equal to M times V, the momentum of this boxcar, so I'll just write down M1 times V1, and the momentum of that boxcar, M2 times V2, should equal to the momentum of the combined system. So I'll represent that as MC VC. So I chose the subscript C to represent combined. Another way to think about this, given that the sum of momentum vectors must all add up to 0, is that once they combine at this point, the velocity will change. In fact, it might even slow down given that there was a difference in velocity in the first place. So to make sense of the idea that the sum of momentum vectors must all add up to 0, we can say that the combined momentum would have a slower velocity than these two. So it would look something like this. But if you don't like this model, you don't need to think of it this way. Just think of the fact that the before momentum should equal to the after momentum. So this is what I was referring to, plus MC negative VC. So I represented that the fact that it's slowing down as negative VC. And if you were to rearrange this, you would end up with that expression. So if you don't like this, let's just ignore it and continue on with the idea that the before momentum should equal to the after momentum. Okay, now substituting everything that we know, we have 3,000 kilograms, and you can represent the units as well, it's important, times a velocity of 3.0 meters per second, plus this one, 1,000 kilograms times 5.0 meters per second is equal to the combined mass of 3,000 plus 1,000, which is 4,000 kilograms, and the speed is what we're looking for, right? The resulting speed. Next, let's calculate this. This equals to 9,000 kilograms times meters per 1 second. That equals to 5,000 kilograms times meters per 1 second. We'll add those up in a moment. And that is 4,000 kilograms times V. Combining these two is 14,000 kilograms times meters per second. And on the right side, we have 4,000 kilograms times V. Of course, this is a very simple algebraic problem from here. We just divide both sides by 4,000 to isolate for V. And if I divide both sides by 4,000, right, this and this will cancel out. And 14,000 divided by 4,000 is 3.5 meters per second. So that's the answer to part A. In part B, rain falls into the open boxcar so that the mass increases at 1.0 kilograms per second. Now if you read this, that's a lot of rain. 1.0 kilograms per every second. Wow. What is the velocity of the boxcar after 500 seconds? So first of all, let's calculate the momentum of the boxcar once they're combined. So the momentum of the combined system here was what we found as 3.5 meters per second. So the velocity times the mass Remember, the mass of the first one was 3,000 and 1,000. That makes 4,000. So let's multiply these out. 3.5 times 4,000 makes 14,000 kilograms. Forgot the unit here, kg. Kilograms times meters per second. So that is the momentum for the combined boxcars. And again, using the same logic as before, we'll write down P combined is equal to P after. So the momentum after the rain has fallen. Let's see how much mass will accumulate after 500 seconds. So if we multiply this by the rate of 1.0 kilograms per second, the units here cancel out and we're left with 500 kilograms. Now adding this value to their combined mass already, remember the mass was 4,000. So combining these two values, we get 4,500. That will represent the mass part of the right side. So momentum is equal to mass times velocity. The new mass after 500 seconds is 4,500. We're looking for the velocity change, so I'll write down delta V for that. And we already found that earlier as 14,000. Dividing both sides by 4,500. Let's use our calculator. 14,000 divided by 4,500 makes 3.1 repeating meters per second. So if the rain continues to fall, and after 500 seconds, there will be a change in velocity of 3.1. Technically, it will get slower by 3.1 meters per second. So there you have it. That is how to find the resulting speed in a conservation of momentum type problem.